Hello and welcome to this CUBES how-to video where we will illustrate how to design an aperiodic frequency selective surface, an FSS, subreflector using CUBES. If you're not familiar with CUBES and don't know how to set up, analyze and optimize quasi-periodic surfaces, we recommend that you see some of our previous CUBES how-to videos where we explain how to define periodic unit cells, generate scattering matrix databases, analyze and optimize quasi-periodic surfaces. We start with the Tigra Tools project where we have a dual reflector system where the subreflector is an FSS. The FSS consists of two layers of square loops separated by a honeycomb and various dielectric layers. It's designed to reflect in Ka band and to be transparent in S band. For the dual reflector systems, the subreflector surface is sometimes not perfect, and this can reduce the performance of the antenna system. The idea is that we want to use an aperiodic FSS to compensate for this. And to this end, we have defined a dual reflector system where the subreflector surface is not ideal and the FSS element is deployed periodically over the surface. If we analyze this antenna system, we see that we get a peak gain of 47.7 dBi. We want to improve this by optimizing the element sizes of the FSS. Using CUBES, we can adjust the FSS element dimensions element by element, or we can describe the FSS element dimensions using spline functions. For smooth varying quasi-periodic surfaces, e.g. aperiodic FSS, spline functions are preferred as it reduces the number of optimization variables when designing these surfaces. Therefore, we proceed by using spline functions. All the analysis objects have been defined, the PO object for the main reflector and the periodic method of moment object for the FSS subreflector. The scattering matrix database that speeds up the optimization of quasi-periodic surfaces has been generated at a previous command. All the optimization objects have been defined, and the goal is to optimize the FSS to increase the peak gain of the entire antenna system. This could be achieved by optimizing the length of the square loops. For the optimization of the FSS subreflector, we need to select how many spline functions that are used to describe the FSS surface. And this is controlled by the knot spacing attribute in the bulk optimization variables object. This attribute is only relevant and shown in the GUI when spline functions are used to describe the FSS surface. The value here is selected such that it corresponds to 6x6 spline functions to describe the surface, resulting in a total number of 36 optimization variables. For simplicity, we'll only consider a single frequency optimization at 25 GHz. We now run the optimization, and after 1 minute 52 seconds, the optimization is complete and we evaluate the performance of the antenna system. The analysis of this optimized FSS subreflector shows a peak gain of 52 dBi, which is more than 4 dB higher than the initial design. If we load the optimized element variables and examine how the elements have been changed, we can now see that we have an aperiodic FSS element layout on one side and a periodic element layout on the other side of the reflector. One could also carry out the optimization without using splines, but rather using the individual element dimensions as optimization variables. This will increase the number of optimization variables significantly, resulting in longer optimization time and providing almost the same antenna performance. For practical applications, one would need to optimize the FSS in multiple frequencies for both S and Ka band. But we hope that this video gives you an idea of how you can use CUBES and spline functions to efficiently optimize your quasi-periodic surfaces. Thank you very much for watching.